Hello, in this video, I explain how to solve this problem. Okay, so this problem. So there is a steel bar, okay, steel bar of the cross section 40 millimeter times the 40 millimeter. So cross section of this one is 40 and 40. Okay, so 40 and 40 and subjected to a UDL, uniformly distributed load, 1 kilonewton per meter. So the length of the bar is given, okay, and one side of the bar is supported by a pinned support and others here, okay. So here we use another bar to support this one that is made up of aluminum and the cross sectional area is given 78.54 and one more force is applied at the free end, okay. So we have to model this one as a, okay, so line body, okay. I am going to use line body for this problem because this one is very um, okay, slender type of body, okay. So slender type of body. So slender, right? Slender means the cross section is very small, okay. The cross sectional area is very small compared to the length of this one, right? Similarly here, so I can model this one as a line, okay. For the steel, one line, and for aluminum, one more line, okay. So one more line, and so these two bars here we connect this one using a pinned support, okay. So using a pinned support, and here also we have a pinned support, okay. So but both are different material and different cross sectional area, okay? Stiffness is different for both of them, right? So we have to model them with a separate lines, okay. It's not a single line body, two line bodies, and we have to join them using connection, okay. So use bonded connection, and after finding the solution, we have to compare our solution with the, okay, so this one is the theoretical values, okay, and also find the reaction force here and find the reaction force here, okay. That is the first problem, and same problem, okay, so same problem I want to do, okay, so I want to do the same problem um, using a fixed support here, okay, not pinned support. So here that one is a pinned support, but this one I am going to use a fixed support, okay. So this on both the cases you can use a fixed support and see if there is any difference in the result, okay. So yeah, but fixed support, giving the fixed support is easy, but the pinned support is a little bit complex, okay. Let's solve using first using pinned support, okay. Before solving that one, right, we have to model this one using a line element, okay, line body. So open the ANSYS static structural, okay, static structural, and yeah. So here we have to use aluminum, right? So by default we have only steel. So change the engineering data. Okay, so you can find from engineering data sources, we can find the aluminum material data, but that takes time. But we need only change the Young's modulus, okay, for this problem. This one is a line body, right? We need to only change the Young's modulus. We don't need to change the Poisson's ratio also, but Poisson's ratio is same, almost same for structural steel and aluminum. Even though it is different, you don't need to change, okay? So only need to change here is, okay, only thing we need to change is the Young's modulus value, because we are conducting static structural, right? Aluminum. Yeah, you can give any name, okay? So aluminum Young's modulus is given in the problem, right? So 69 gigapascals, okay, GPa here, so gigapascals, and Poisson's ratio is 0.32. So actually we don't need Poisson's ratio. We change that one to gigapascal or megapascals if it is in gigapascals, right? So 69, and Poisson's ratio also change. Actually, you don't need to change that one because it's a line body, right? It only calculates the bending stress, okay, maximum combined and minimum combined stress, okay? It's only bending stress. Okay, so engineering data changed, okay? So one is aluminum and another one is steel. Okay. So now in geometry, I'm going to create my own geometry in new design modeler, okay? design modeler geometry because I am familiar with design modeler. So just creating lines is enough, right? So creating line. So you can create using points, right? And connect those points we already learned, or you can create using sketch, okay? So we make sketch, sketching and XY plane. Before that one, right? Change the units to millimeter, okay? Units to millimeter is better, okay? Millimeter is better. And yeah, zoom for the right. So because total length is 600 line, 600 millimeters. You can start from here, 0, 0 and horizontal line. So total length of this one is 300 plus 300, 600. Okay. So you can model that one is a single line. Okay. So dimensions 600 millimeter. And so one more line, right? One more line. But for that one, we need a different sketch because we need a different body. Okay. So different sketch. But if you use the same sketch, right, that will be considered as a single body. Okay, so horizontal line, here vertical line, vertical line. So the dimension of this line is 200, 200, 200. And from here to, okay, sorry, so we need the horizontal distance between this one and this one. So that one is exactly half, 300. Okay, so this one is my sketch 2. Okay, this one is sketch 1 and this one is sketch 2. Sketch 1 and sketch 2. Okay, so now create a line body from sketch 1, right? So create concept lines from sketches. Okay, so lines from sketches. So the name of this line body is, okay, you can change that one later. Okay, sketch 1 and add material or add frozen. Okay, first body, right? Generate. Okay, one body is created, just only this one, right? And yeah, select sketch 2 and concept lines from sketches again, and select this one already selected, right? Apply and generate. Okay, so line 2. So we have, okay, sorry, and here we have to edit this one, right? We need to use add frozen, okay, because there are different materials. So two line words, okay. If you use add material, right, that will be considered as a single. And I can rename this one, right? So rename to avoid confusion. This one is a steel body and this one is a aluminum body. Aluminum body. Okay, so yeah, now we have to assign cross section, right? You can give in model also, but I am doing here. So cross section. So 40 millimeter times 40 millimeter, right? So rectangle cross section. So concept, create a rectangle cross section. Okay, rectangle cross section. So 40 millimeter times, okay, not 40, 40 millimeter times 40, 40 millimeter. So be sure to be in millimeter, right? So sometimes you are in meters, right? Then you have to give 0.004, okay, 0.04. And yeah, so assign steel body cross section 1. Again, concept to create cross section, right? Again, you can create rectangle or circular cross section. So for this one, right? So only cross section area is important because this one is in only in tension, right? But this one is in bending. So only cross section area is important. So you can calculate. Okay, so diameter or radius, or assume that is also rectangle, square cross section, right? Square cross section size is this one, the square root of this one, right? A square is equal to 78 point, so 8.86279 millimeter, right? So you can copy that one, exactly same value. And yeah, concept cross section rectangle and you can give this one 8.86 something, right? So same cross section, and assign aluminum body cross section 2, rectangle 2. Okay, so rectangle 1. So be sure here steel body rectangle 1 cross section, right? Rectangle 1 size is 40 times 40. So rectangle 2 cross section 8.86. Okay, aluminum body 8.86 and 8.86. So rectangle 2 cross section is assigned. Okay, that is our model. Okay, so we have to have two bodies. Okay, here two bodies because both are different material. Even though cross section area is different, okay, you have to model with the two different bodies. Okay, for example here, right, I model this one is a single body, but here from here to here one cross section, or from here to here another cross section, you have to model that one with two bodies. Okay, not a single body. Okay, okay, then yeah, geometry is finished. Okay, geometry and finished. Okay, so now yeah, engineering data finished and geometry finished and model, right? Okay, so model. So wait some time, it is taking some time. Yeah, in model, first thing you have to do is assign materials, right? By default, it assigns structural steel, right? So yeah, for steel body, assign steel material, structural steel automatically there. You don't need to change anything. But for aluminum body, this one is should be assigned to aluminum. Okay. So yeah, steel body, structural steel, aluminum body, aluminum. And now we have to connect these two, right? So how you do? So use connection, insert manual contact region. Manual contact region, you can use bonded connection. Okay, that means these two are like welded or riveted here or something, or using bolted nut, right? That is bonded. Okay, whatever will be the displacement here, that is applies to here also. Okay, so that is target or contact. Okay, so one more thing is target or contact. So two are different. Okay, so contact is here and target is here, or target is here and contact is here. So you can see, right? So blue color is target and red color is contact. Okay, or red color you can change, right? That one interchange, no problem. One should be target and one another should be contact. Okay, and now mesh, I am going to use default mesh because the line body you don't need to worry about mesh size and all. Okay, and now yeah, what I have to do here is um, okay, so here um, yeah, apply load here 10 kilonewtons and apply here what pinned support, right? Pinned support means, so the displacement along x direction is 0. So delta x is 0 and the displacement along y direction is 0. Okay. And the displacement along z direction is 0. Okay. So z direction is 0. That one is displacement completely 0. And also, yeah, pinned support means it can rotate about the z axis. This is a z axis, right? So plane x is normal to my paper. Okay, I see normal to this plane, right? So it's z axis, so only that is free. Okay, so theta z is free, but I am not allowing this one to rotate about x axis. I am not allowing this one to rotate about y axis. So this one is y axis, right? I'm not allowing to rotate about this axis, and I'm not allowing to rotate this one, only in z direction free. Okay, because this one is z axis, right? It is free. So that is pinned joint. Okay, so pinned joint. So here also pinned joint. Okay, so pinned. So like this means it's a pinned joint. Okay, pinned joint. Okay, so you can give what you can give, right? So to give pinned joint, okay, here insert, right? What type of we have to give, like displacement. Okay, displacement means that only gives displacement. Okay, the delta x 0, delta y 0, delta z 0, and also fixed rotation you can give, right? Fixed rotation means you can arrest theta x, theta y, theta z. But I'm going to use remote displacement. That means I want to give all the things at a time. Okay, so here x is not free, right? X component is not free, so zero displacement. Y component zero displacement, Z component zero displacement, and yeah, rotation is zero about x-axis, rotation about y-axis zero, and my z-axis, right? This one, so it can rotate. I mean, it can deform like this one, right? So I'm not, I am allowing this one to rotate about z-axis. So this one is z-axis, right? Okay. So z-axis. So a z component is not zero. Okay, free. Okay, free. And yeah, where? At this location. So similarly, yeah, you can apply fixed support or remote displacement for this, because that is just only subjected to tension, right? Only it deform up and down. So you can also use fixed support or remote displacement for more representing, correctly representing this one, more correctly representing this one is the pin support. So yeah, same here, 0 0 0, and yeah, x is 0, rotation about x 0 degrees, and rotation about y axis 0 degrees, and it's free. And yeah, so I gave the boundary conditions. Okay, so here, right, pin support, here pin support, and now apply 10 kilonewtons load, right? So insert, right, what I can give, like a force. Okay, there are many things here, right? Force. Okay, force. Apply. Yeah, vector wise or components wise. Okay, because I know the y component. So y component is minus 10,000 newtons. Okay, so because it is acting downward, right? So minus 10,000. Okay, minus 10,000 newtons. So at this point, similarly here, yeah, on the bar, right, steel bar, there is a distributed load. So distributed load can be given by line pressure, right? So select this bar, okay, and so insert line pressure. Line pressure means distributed load, and that is also component wise, okay. And so yeah, this one is 1 kilonewton per meter, means 1000 newtons per meter, 1000 newtons per meter, okay. So you should be very careful with the dimensions, right? So 1000, 10th, so 10th, 1000, okay, and a minus, it is acting downward, okay. So yeah, these things, remote displacement, because it's a pin support, right? Remote displacement, force, line pressure, okay. And yeah, so what I want to solve, okay, so beam tool means it will give the, like, direct stress, okay, like tensile stress, okay, and minimum combined stress and maximum combined stress, minimum bending moment, okay. So like we have a formula, right? Sigma is equal to plus or minus, okay, mc by I, okay, or my by I, maximum bending moment divided by sigma, right? So not maximum bending moment, because along the bar we're calculating, right? So bending moment there, and this one is the cross section, right? So rectangle cross section, distance from the centroid to outermost layer, okay, and I is the moment of inertia, okay. So yeah, plus means maximum, minus means minimum bending, okay, minimum combined stress, okay. Combined stress means including the axial also, okay. So yeah, so those things I want to solve, and I want to solve for also deformation, total deformation, and I, in this problem, I want to find the reaction force here and reaction force here, okay. So okay, so insert, okay, here in solution insert probe, okay. So what a force reaction, right? Force reaction at remote displacement 1, right? Remote displacement 1 means here, okay. So And similarly, I want to find force reaction, right? So probe force reaction, right, at remote displacement 2. And also I want to find moment reaction, right? So because reaction means there are forces and moment. For this problem, there is no moment reaction, okay? There is no moment reaction because, it's a fixed support, right? So remote displacement, okay. It's not a fixed support. There is no moment reaction. Probe, moment reaction, okay. Yes. So yeah, those are the things I want to find force reaction. What is the reaction force here and what is the reaction force here and moment reaction. Moment means reaction moment, right? The rotational opposite effect, okay? Yeah, and these things, okay? Yeah, main thing here, right? You have to connect these two bodies, okay? And assign material correctly and apply remote displacement, okay? So you can use fixed support also. You don't get much difference, okay? Yeah, solve, okay? Solve. Yeah, so um, okay. So direct stress means it only gives the tensile stress sigma by A value, right? Sigma by A is okay. So change the units to millimeter, right? I want to get the stress in megapascals, okay? Um, Megapascals or millimeter, okay? So 262, okay? So you can compare, right? So this is subjected to tensile stress, as I said, right? Okay, so these are the results, theoretical results, right? So you can use sigma is equal to P by A and find the reaction here, right? Reaction, and A is this one. So then I get that one is 262, okay? 260. So it is a tensile, right? So that's why we have plus, okay? So P by A. And the bending moment, right? Maximum bending moment occur here, right? Maximum bending moment occur here. So that one is 285.46, okay? So like the bending stress changes like this one, right? Bending stress. So here maximum bending stress. Okay, let's see what is our bending result, okay? Okay, so where is, okay. So yeah, so we are getting the correct result, right? So 262 is minimum combined and okay, so minus 282, that is compression stress, and tensile stress is 306. Okay, so you should get that is also like minus 282 because we have here, right, this together, that's why we're getting like, so actually you should get around 282 only on this, right? So for example here only, okay, only at the bottom, not here, okay. So you can just only calculate um, maximum bending stress, okay, maximum bending stress. Yes, maximum bending stress 282, right? 282. So that is matching with theory, okay. Actually 285 we're getting, right? So 282. So you can further refine this one message, okay, but there is small mismatch, right? So between our result and, okay, anyway, you don't need to change, okay. So 282 and 285, not much difference, okay. And force reaction here, right? So actually you should get around 10,000, okay, minus 10,000 according to theory, minus 10,000. Here some force we can apply, right? Sigma fx is equal to 0, sigma fy is equal to 0 to find force reaction. So minus 10,000 here, right? So minus 10,000. And RD here is same, 20,600. Okay, stress is nothing but 20,600 divided by cross sectional area. So 20,600. So you will get the same answer. So this stress, right? This is nothing but 20,600 divided by this cross sectional area. So yeah, moment reaction is 20,000 20,600. Actually 20,600, but hence is right. Just calculate extra approximate results 20,583. And moment reaction, right? Almost zero, negligible. Okay, because pinned support is freely allowing, right? Freely rotating. So there is no moment reaction. Similarly, here also there is no moment reaction, almost zero. So you see 10 to the power minus 10, 10 to the power minus 10. Okay, that is about fixed support. Okay, sorry, pinned support. So we got right. Remember this value 282 point something. Okay, maximum bending stress. This one we designed for this stress. Okay, so 282 for this one. And I mean when I apply load, right, 282. Stress in this material is 282. Okay, so yeah, now change the, so this one is not a remote displacement anymore. Apply fixed support. So case two of the study is what? Apply a fixed support and see if there is any difference. Okay, so fixed support is very simple, right? You can so select that one and insert fixed support, and same here, select that one and insert fixed support means we are arresting all the degrees of freedom. So there is no deformation and there is no rotation. Same here, there is no deformation and there is no rotation. And yeah, because you apply fixed support, right, you have to change according to what is the boundary condition at fixed support. Okay, so same here, yeah, this one boundary condition at fixed support 2. So moment reaction I want to find, right, fixed support and moment reaction at fixed support 2. Okay, and solve it again. So we got right around 282 when we apply pinned joint. Okay, pinned joint, and solve it again if you by considering fixed support. Okay, so fixed support, you will get, I think, almost same result. Okay, so same result because it's long, right? It's long enough, and you get almost same result. So 275. Okay, direct stress is a little bit different. Okay, so in this case, in our case, right, direct stress means tensile stress 262, but here it changed. Okay, when you apply fixed support, it is 275 because the reactions changes here, right? So stress changes, but bending almost same. Okay, so and yeah, reaction forces also changes. So here for fixed support, right? For pinned joint, we have minus 10,000, but here 11,000 or something. Okay, and same here 21,000, right? Okay, there 20,000 something. Okay, and also we have moment reaction here. Okay, here jet moment reaction, right? 32,000 something. E5 means, right? Not 30, that 320,000. Okay, same here. We also have moment reaction about z axis 3325. Okay, so yeah, those are the things, different things. Okay, small change in answer, right? But actually you to represent this figure, right, this is the actual case, so we have to apply not fixed support, we have to apply. Okay, so only the rotation is free here, right? So if you apply fixed support, right, rotation also fixed. Okay, so that is the end of this one. Okay, I'm closing this one. Thank you.